In this air resistance lab, we're going to model the motion of an object that's a two-dimensional projectile. But this time we want to consider not just the free fall motion of it, without drag. We want to include drag as well. Let's see, to quantitatively study the effect of drag on the motion of an object, we need to quantify what we mean by drag. Drag is a force that acts to oppose the motion of an object through a fluid. And air is considered a fluid. So the force depends on the parameters of the system, and there are several of them. All right, so it says, what parameters do you think drag depends on? Imagine an object moving through air. Like, what variables might affect the size of this drag force? And you often want to think in physics about the limit of a situation, like the extreme. So what if your projectile just wasn't moving, Would there be a drag force then? No, of course there wouldn't be, right? So if we're at rest, then the drag force, F air or F drag, equals 0. So that's something to consider when you're thinking about the formula for drag. But when we're moving, we do feel air resistance on us. So the point is the velocity or the speed plays a part. And so it says often all the parameters affecting drag except the speed of the object are lumped together into a single number called the drag coefficient. Some of the other properties would be like the surface area, for example, of the object that's moving. So it says the dependence on speed will be determined in the following activity. At terminal velocity, we find that the drag equals the weight. So what does that mean? It means when an object is just at rest at the peak of where it's being released, then the drag force is 0. But once that object starts to fall, like off a cliff or something, as a motion map, what it'll look like is it's going to pick up speed and then pick up some more speed and then more and more, but eventually it'll reach a condition where it starts to go with constant velocity. And so if you were to look at like a velocity versus time graph for this, what you'd see is like, yes, your velocity would start to increase with 9.8 times t. Like that would be the formula that it would start to increase with, right? But it doesn't keep increasing like that. What happens is this. It levels off. And then you reach a limit. Or you approach a limit, which they're calling here VT, the terminal velocity. So what does the acceleration do then? It starts off at 9.8. It could go down something like that towards 0. Is the idea. And in this coordinate system, I'm choosing up to be like the negative direction. So I'm just showing like the magnitude here. Because I know usually I put velocity down if it's negative and acceleration down if it's falling down. anyway, that is that. So all right, let's try it. So we want to create a spreadsheet. And it says, imagine a baseball being thrown vertically upward at 35 meters per second from the top of a cliff 45 meters above a river. All right, so let me... It just seems like this should say F drag is proportional to VT squared. Not sure if that's what they meant. Anyways, let's see. Now we've got a baseball being thrown vertically upward from the top of a cliff, so 45 meters. Person. Let's see. And they're going to throw it up. So we're going to have this kind of motion map. All right. Now we're going to ignore drag first, and we want to calculate the time that it takes for the ball to reach the river below. It's got VI y equal to 35. Oh, determine the time it takes, yeah, to reach the river below. So I'm just going to change the numbers for the purposes of my example. Let's change it to 50 meters per second. And let's change this to 100 meters. So it's a similar example, but not the same. All right, so for me, what I would do to solve that is I'd say, all right, if we want time, we'll do delta y equals 1/2 AT squared plus VIT as one option. In this circumstance, some people would prefer to use the delta V equals AT. Let's see. Or they may wish to use even VIY squared plus 2A delta y equals VFY squared. I'm going to try it with this one here. So using this one, I would do negative 100 equals 1/2 negative 9.8 t squared plus 50 t. And then since I have a quadratic, that's something I could solve using quadratic formula. So negative 100 equals negative 4.9 t squared plus 50t. Should get all the terms on the same side. And you can do 0 equals negative 4.9 t squared plus 50t plus 100. You could switch the terms, signs if you wanted, making the a positive. And then you're supposed to plug into quadratic formula, which is negative b plus or minus square root of b squared minus 4ac over 2a. So t is negative 50. T equals negative 1.71 seconds, or t equals 11.9 seconds. All right, so we obviously want the positive of that. Basically, if we do our stack of motion graphs, and I do AY and VY and Y, then for this we're going to see a graph that looks like that. Our velocity should do something like this, like that. Acceleration would be like that, so that the peak lines up with the 0. That's everything, from the past. That's the way we did it in the past, And so apparently the times that I'm given are here, and also if you extrapolate this back, that's where the negative comes from. So negative 1.71 or 11.9. So this just gives me a sense of what I'm looking for in my spreadsheet when I set it up. It says our ultimate task is to create a spreadsheet that can solve a problem like this one when drag is included. But first we'll do it without drag just to see if it agrees with what we found theoretically there. Let's see, so if the spreadsheet passes this test, then we'll try to add drag to the spreadsheet and use it to solve problems where an answer can't be calculated by hand because the forces are all changing and it's just like too complicated. So let's see. Equations used to solve the above problem in the way that I did are only valid when the acceleration is constant. And since drag leads to a non-constant acceleration, they're not useful if the ultimate goal is incorporating drag. And so instead, what we'll use is a general technique for solving any motion problem, no matter how complicated, is modeling it with the spreadsheet like we'll do here. So in this approach, we will apply the basic concepts of motion in a step-by-step incremental manner. And it says, in a nutshell, the velocity of an object at one instant can always be determined if you know the velocity of the object at a previous instant and the acceleration, which represents the change in the velocity. So here they're showing kind of like a calc difference quotient is what it is. And they're saying that the acceleration could be given by the velocity at a future time minus the velocity at a current time divided by the change in time. So what does that mean for our situation? Let's see, our velocity started up high at 50 meters per second. But it didn't stay 50 meters per second. We saw that it was going to head down. So they come up with a delta t, if this is the t-axis. Then here, this represents a delta t. And the initial time could be just t. And then this new time would be t plus delta t, is what they're saying. All right, and then that would lead to a velocity here, where this height is v of t, And this height would be v of t plus delta t. And they're just saying, basically, if you were to create a triangle out of that, then the rise of the triangle here would be given by v of t minus delta t minus v of t. That would take care of the sign, because the sign here should be negative since we're going like over and down. All right, and then if we make a slope out of that, then we get the acceleration. So they're saying the acceleration at time t is not exactly equal to this quotient, but it's approximately equal to it. What we could do, though, is rearrange this formula to solve for the new velocity. Which is this one. So solve it, and you get this. Move this guy to the other side, then add the other guy. You get a times delta t plus some current velocity v of t. So what does this represent? It represents the acceleration at the current time This is going to be an incremental change in time. And this represents the current velocity. So with these things, we can solve for the new velocity. All right, hope that makes sense. And then they do kind of a similar thing here with the position. We know that velocity is the derivative of position with time, so the same kind of principle holds. All right, so it says here that these equations are only approximations. They would become exact if the limit of delta t were to become 0. However, we won't do that in our spreadsheet, of course. We'll come up with some real delta t which is small. And if it's very small, then it can be a really good approximation of the true velocity and the true position of the object. Alright, so it says input the initial time and initial position and initial velocity, all that stuff, into your spreadsheet. They give you a mass of the baseball, and for this problem, assume the drag coefficient is nothing because we're not going to include drag the first time. And use a time step of 0.05. Now it's saying here, could you, for each of the 4 calculated columns, write the appropriate Excel formula needed to calculate the next row. Let's see, first row is determined by the initial inputs. Alright, so let me go to Excel here for a minute. Alright, so here's a brand new spreadsheet. So I'm going to start this off saying that there's going to be several trials, so I'm going to say that this is incremental. Maybe before I even do the incremental version of it, I might do like a version just not incremental. And the lab doesn't ask for that, but I just want to show the difference. So this would just be according to the formulas, and it's not incremental. All right, so we'll have a column for time is important. And then we want a column for acceleration, velocity, position. All right, now our time increments were going to be 0.05, like over here. So what I'm going to do is I'm going to put that in and then start counting by 0.05s. And in Excel, I can just start a pattern and then just drag it down. And it'll just keep going. Don't know how much time we'll need yet. But what I'm saying is that for my formulas, I'm just going to keep those same times. Now when we're in free fall, we just want negative 9.8 to be our acceleration. Just all the time. And we're not including drag, so this is just according to the motion formulas that are derived from calculus. Now, our initial velocity goes here. I'm going to say it's 50 for my problem. And then we also started at 100. So those are my initial values. It would be the same for my incremental as well. All right, now we want to think about what happens to the velocity as time goes on according to the formulas, and what even is the formula, right? So for velocity, we would want to use the formula v final y equals ay times the time t plus viy. That's a formula we had used in the past for motion of a falling object that's accelerating. And so you want to type that into Excel, and we could say, okay, let's do a new calculated column. So for our acceleration, we could call up a cell, but we don't really need to because we know it's going to be constant the whole way down. So let's type it in, negative 9.8. And then we'll do times t, and that I actually do want to call a column up for. I'm going to call it $C. It's $C11. Yeah. So I'm calling up the current time according to my time scale there. And then I want to add in the initial velocity, which comes from the cell above. So for that, I'll put in E. Oh yeah, you don't even have to do dollars in this. So I guess I don't even need that really. But I do need a dollars in this one. Why did I put the dollars there? Because I want to lock on the initial velocity. That's an important number. And I have to put the dollars so that it stays with that cell even if I drag this down. So okay, we can see the velocity is decreasing. All right, so just keep dragging it down, and we'll see if we could find when there's an important change. Might have to go way down. Okay. All right, so it looks like the velocity reached 0, close to around 5 seconds after the launch. Let's drag down some more, because we're looking for it to match up with the formulas. But one other thing we have to include is the position. So what formula do we use for position? Well, y final equals 1/2 a t squared plus v I y t plus yi. That's the motion formula we used in the past for position. This is going to be our initial position, so we want to just type that in the next cell. So 1/2 negative 9.8. We'll call up looks like C11, yep, again. And then we have to square that, so get that. Then we want to call up E10, which was the initial velocity, but it's got to be $10. Should be $10 times C11 plus F$10. All right, now look, our projectile is moving upward, which is what's expected, you know. And hopefully it'll come back. Well, hopefully, first of all, it'll reach a peak when the velocity becomes 0. That's what we're looking for. Yeah, okay, perfect. So right around here, there's an important thing happening. This would be considered the peak, the closest approximation to it. See, here we're at a velocity of 0, and this is the highest position that our projectile reaches. All right, now we can keep going and find some other important things. There should be a time when it comes back to the same height that it was launched from. And that'll happen when the velocity ends up being the negative of the initial velocity. So it's back to the launch elevation. And then just want to keep going to see when this thing hits the river below. Okay, right there is the closest approximation to projectile hits the river. That is just connecting the past motion formulas with the spreadsheet and trying to make sense out of what's happening in the sheet. And look at that. The time of it hitting the river below exactly matches what we had said theoretically in the formulas, you know. All right, so now that I showed that approach, hopefully what I'll do next will make sense, because it's a different approach. See here, every cell depends only on the time and these initial parameters, these like initial motion constants. In the one on the right, though, it's not going to be like that. Each cell will depend on the previous cell. All right, so what do I mean by that? Well, the acceleration here is still going to stay 9.8. So we can actually just Copy that down. That we won't mess with this time. Looks like I better go farther with this. All right. But what about the velocity? Well, let me copy the formula correctly here. So we're looking for new velocity, v, equals the current acceleration times delta t plus the previous velocity. Okay, so how do we type that into Excel? You want to say it's going to be equal to J11, the current acceleration, times your delta t, which is 0.05, and then add that to the previous velocity, which was k10. All right, so just to be clear, this is the current acceleration. So current velocity equals current acceleration times the delta t plus the previous velocity. And it all just comes from this one. Current acceleration times delta t plus. Interestingly, you can write it like it is written there, but the way we're doing it in Excel is basically v of t equals a of t. But you know what? We could make a slight correction, which would be even better. A of t minus delta t times delta t plus v of t minus delta t. And what is that? Like, what's the difference, right? So this one would say that the current velocity is equal to the previous acceleration times the delta t plus previous velocity. It's the same concept, but this works a little better with Excel, right? I mean, that's basically the way I'm entering it. So I'm just going to make a slight change with my spreadsheet to call up, instead of the current acceleration, I should call up the previous acceleration. All right, so instead of J11 then, switch it to J10. All right, cool. I mean, here we get the same answer either way, but it could make a difference in the future. All right, so those are the velocities. Let's drag that down and see if there's similarity in the numbers. Yeah, I mean, they're so similar. Basically the same. All right. Final velocity, negative 66.62. Final velocity, negative 66.62. So both approaches are working well. And, you know, just to make it clear, Excel is going to advance that. So, like, when you go to the next one, it's going to take the 49.51 and then multiply the acceleration times delta t to get the new cell. Anyways, what's next? Now we should do the position. Okay, so how do we do that? To get the current position following the same pattern, we would want velocity times time plus previous position. And we just copy what we did and adapt it for position. You'll find that y of t plus delta t will equal the velocity times delta t plus y of t. So new position equals current velocity times your delta t. This is going to be, well, let me write the formula first. Oh, and I want to change that. Okay. So we'll do previous velocity times delta t plus previous position. And it's a subtle thing, like whether you use the previous acceleration or the current acceleration there. Like you'd really pretty much get the same answers, but anyways, let's try this. Okay, so let's do previous Vy, which will be K10. Yeah, that's our velocity previously, 50. Multiply our delta t, 0.05. Add in the previous position, which would be L10. So as you can see, the cells we're calling up are from the previous line. And then when you do it here, you're basically doing K11 times delta t plus L11. So see, we're calling up the previous cells each time. So we just keep dragging that down. And we want to see that this is similar to that. But they are not exactly the same. And that's because this is a discrete calculation here on the right. And the other one is based on like a continuous calculus formula. But there are similarities, certainly. All right, with the incremental approach, it looks like our peak, our highest point happens right about here, or here. You could say the velocity is 0 there. If you're going by the position, though, looks like that is the highest number. So there you go. I mean, the peak is, only 0.05 seconds off of what we thought the previous approach peak was. Yeah. So that's pretty good. Oh, yeah, well, just a little bit over a meter higher, yeah. All right, how about when we hit the river below? Yeah, right about there. Projectile hits the river. All right, enter the correct formulas, complete the spreadsheet, create a graph of position, velocity, and acceleration versus time. I'll go to insert. We could do a scatter plot. And you'll want to, let's see, grab your time as your x, this, and then you want these as well. Let's see, scatter plot. All right, yeah, I mean, that's pretty good. So this is the position graph. All right, so there's that one. I'll put it like over here or something. Okay. Okay. Insert scatter plot. Okay, that's pretty cool there. We can go ahead and just put our velocity graph right under our position graph, line them up. That's awesome. And you want one more acceleration. Grab those. All right. All right, just what we expected. Now, that was the theoretical, of course. You could do the same thing for your incremental, but they're going to just be the same, pretty much. All right, so now let's go on to make a new one. Incremental with drag. Still want to copy the time down. All right, but now, since we're including drag, the acceleration will not be negative 9.8 the whole time. So let's go back to the lab and see what it should be. Yeah, it says here that we can calculate the drag force, like the strength of it, by this constant, this coefficient b, times the speed squared. The force will always be directed opposite to the object's velocity. So what does that mean? It means at the beginning, when the person throws the ball up, the ball's going to be moving when it leaves their hand. It's going to be moving pretty fast. 50 meters per second in my example. And what they're saying is there's going to be a force directed opposite that. Now we know there's always a weight to it, but not just that, but now there's another force too. The drag force. And what they're saying is, like, if the object's velocity, v, is positive, so up, then the drag force will be negative. So if your object's moving slower, you'll still have the same weight, W, but they're saying that the drag force would become dramatically smaller. And then, when you do get to the peak, you'll be at rest. And you'll still have your weight. Earth's not going to stop pulling on your object. It's still going to pull. But you won't have any velocity and you won't have any drag, because you're not moving. Then your particle is going to change direction. Velocity is going to go down this time. And the weight remains what it was. But the drag force switches direction. Now the drag points up, because the drag is always opposite the velocity. All right, and down here we will have a weight. And we'll have this. And like this. Alright, so that's the story of what the drag is doing. And if you check out, let's say, this formula here, it says F drag equals negative BV squared. If the velocity is in the positive direction, then what direction would this equation produce? negative, right? So that would work. The problem is, like, what if the velocity was negative? You'd square it, and you'd still get a negative. So, like, that wouldn't work, is what they're saying. And this one wouldn't work either. Because if the velocity was positive, then your drag force would be positive, so that's not what you want. They're saying instead that this equation is what we want. What this does is it absolute values just one of the variables there, but it leaves the other one so that it can include a sign. In like some textbooks and such, they don't put the y on there. I always do. Just from Calc 3, like, you have to put a y on there to say that it's in relation to the y-axis, so it could be positive or negative. See, in Calc 3, if you just put v, that means magnitude of velocity. But for some physics textbooks, just so you know, when we're dealing with just one-dimensional motion, they don't put the y on there. They just assume it's implied that it could be positive or negative, which I think is a confusing convention. But I'm going to put the y on there, and then this will have a y as well. This will be a component of velocity. Anyway, that is the formula that we want in our spreadsheet. All right, so we can create a column for it. Let's type in my acceleration, velocity, and position. We could even include a column for the weight. Column for the weight, column for the drag force. Now, you may want to make a column with your mass, perhaps, because now the mass matters. It's just going to be a constant. I think they said 0.145 kilograms. So that's that. Now we want the weight, which is the mass times g. So I'll just do W10 times g. It's up to you if you want to make it negative or not. I'll just say that it's going to be just the magnitude of the weight, positive. Alright, now for our drag force, we may want to make a column for the drag coefficient. And if you want, like, you could put the drag coefficient somewhere else if you don't want to have like a whole column. It doesn't matter. But let's see, what drag coefficient do they want to use? 1.2 times 10 to the minus 3. So 0.0012. That's what they gave. Let's see, so drag coefficient is B. That is the letter given to it. Mass M. Weight mg. And now the drag force. So the formula for it is F drag equals B times V times absolute value V. but then we put a negative in there, and I'm going to call it Vy because I like to include the y. Alright, that looks good, and we can type in our initial velocity, type in our initial position. That's all fine. It's like our starting inputs to this. Now, when it comes to the drag force, though, we want to call up W10, which is the drag coefficient, and we want to multiply by AB10, which is that velocity, and then we want to multiply by the absolute value of AB10. Oh, I need my negative on there. Alright, now we have the drag force. Now we should make a new column for the net force. Okay, because the net force is the thing that really determines the acceleration of this projectile. It's not just the weight that does it, it's not just the drag force. What we can do then is sum them together, but keeping in mind that the weight needs to point downward. So I could do negative mg, which would be negative y10, plus my drag force, which would be z10. Alright, that gives me supposedly the net force. I've got to drag all these columns down, but there's a problem. When it comes to the drag force here, like, you can't calculate the next row because you don't have a velocity there. So what we'll have to do is, let's do it step by step then. Let's find the acceleration from the force. Instead of letting my acceleration automatically be negative 9.8, I'll take the net force and then divide by the mass. Alright, so that's that. Now let's use that acceleration to find the next velocity. So what formula did I plug in, by the way? I plugged in A equals F net over M to get that. Now for my velocity, I'm going to use that same idea of Vy equals, and this is AY, by the way, Vy equals previous AY times delta t plus previous Vy. That's what I did in the other example. So let's type that in. Previous AY is AB 10. Multiply by 0.05, the incremental time. Then add the previous velocity, which would actually be the cell above me, AC10. And look at that, it changed the velocity just a little bit based on this acceleration, which is an extreme, it's a large acceleration. Larger than 9.8 is the idea. But now what's cool is now, because we have a new velocity in that cell, we can calculate the drag force, see? So it's like one plays off the other, and then the other plays off the previous one. So now our drag force will be found by your coefficient times your velocity times the absolute value of the velocity. You get a new drag force. Now you can calculate a new net force. And because you now have a new net force, you can now calculate a new acceleration. And the acceleration is changing. Alright, so if we take all this now and copy it down, let's see what happens. So our velocity goes to 0 right about here. Yeah, that's an important one right there. Alright, so supposedly this should be the peak, which is different from the other time that we'd found, see? So using no drag, the peak occurred at 5.15 seconds. Over here it looks like our peak is occurring much sooner. Because of the effect that the drag has on the projectile, at 3.35 seconds we reach the peak. Alright, then our velocity does start to go down, a downward direction. And it's picking up speed, right? But you notice over time that the amount that it picks up becomes less and less. And you might think about, like, what's the meaning of, like, why the changes are becoming, like, less and less extreme. It's like it's not changing at all after a while, you know? And even check out the acceleration too. It's really big in the negative direction because it doesn't like going against the wind. And then at the peak, it reaches an acceleration of negative 9.8 because there's no drag at that time. So that's what you want to look for to see if you're doing it right, you know? And then, okay, now we're accelerating downward, but the amount that we're accelerating is becoming less and less in size. And eventually that acceleration like levels off to where there is practically no acceleration. You might think about, like, you know, what's the meaning of that? But to really see it in the graphs, we can go to our position calculation. So you just want to do it the same way as I did it before, which is the new y equals the previous velocity times delta t, and then plus previous y. Alright, so previous velocity is AC10 times delta t plus our previous position, which is the cell above me here, AD10. That way I'm using the velocity to calculate a new position. And then we just drag that down. Now we want to see that our highest position here happens around the time that the velocity is 0, so you could say that if we're going by the graph of the position, that this is the highest position. Alright, then we keep going. And it's interesting to see where it comes to the river bed here when it strikes ground. Looks like right here the y is 0. So here's where it hits the river. Let's compare that to the other case. Alright, so here projectile hits the river later without drag at 11.9 seconds. With drag, it hits the river 10.65 seconds. So it'll be really cool to create a graph out of these new points. So let's do time and acceleration. Insert graph, scatter plot. Alright, let's go farther with it. Okay. Alright, it's an interesting acceleration graph. Certainly different from the types we had looked at before. It's a changing acceleration. They call it change in acceleration jerk. So there's definitely some jerk going on there. Starts off at -30. When the projectile reaches its peak, we're at 9.8 for a bit. Then it looks like our acceleration heads towards 0. So the acceleration stops. Alright, let's do time with velocity now. Alright, a similar graph to what we would have expected. But it's not exactly a straight line, is it? And wow, look at that. Okay. So we're starting off being thrown up into the air. We reach our peak here. And then it looks like our velocity is heading toward the negative like we'd expect. But it's not a straight line. Oh, there. Yeah, see, it's not going to just keep going toward negative infinity. Alright. Yeah, it levels off. So what's it doing? It's terminal velocity. It's reaching terminal velocity of around 33 is what's happening. Yeah, that's pretty cool. Okay. Now let's try a position graph. Alright, there's our graph. We reach a peak, come back down and hit the river. Now, if it goes beyond the river, though, it's showing that it would continue with this constant velocity. How do I know it's constant? Because here it's concave down, it's curved. But in this section, you can see the position heads toward a linear shape. And if the position versus time goes linear, then you know you're at constant velocity. Alright, so I hope that explained that. There is a two-dimensional part to this as well. Alright, now what we want is drag in 2 dimensions. So let's say that a baseball is traveling at 50 meters per second at a certain angle, 53. It's going to have an x and a y component. VIX and VIY. says here, to handle two-dimensional drag, you'll need to calculate the x and y components of the variables. And we'll have to create separate columns for ax, ay, vx, vy, and so on. You'll also need to set the initial values for each of those. Now, if we turn the drag formula into a vector formula, then it looks similar. But there is an important difference, that this, it doesn't mean just absolute value of the thing anymore. It means the magnitude of it. And so that's got to be incorporated into your formula. So I'll just do an example of that. Let's see, so draw a free body diagram for the baseball. Yep. Let's see, so a free body diagram for the baseball during its two-dimensional motion. It's going to have a certain velocity, v. It's going to have a drag force, well, first of all, let's do the easy one, weight. And now it'll have a drag force. But the drag force is directed opposite the velocity always. So if the projectile is on its way up, we'll have our drag being 180 degrees opposite the velocity. And if our ball is headed down, the weight will still be directed down, but the drag force will now be this way. All right. So, how do we deal with that in the spreadsheet? It says you could apply Newton's second law in the x and y direction and then solve for the acceleration. So, all right, let's see. We'll do v. Well, we'll do f net x equals m times ax. All right, so what would be f net x? That would be it would just depend on your drag. Like there wouldn't be any f net due to the weight because that's all vertical. All right, so I guess you're gonna have f drag x equals max. You know? Yeah, so f drag x equals max, and then if we do the y, that's where it's a little different. You'll have f drag in the y. You could do like a minus mg equals may. Right? Because this guy can contribute to the vertical, like it would have its own vertical component there, which would be f drag in the y direction. And then this component would be the f drag x. All right. So we want this and this to be incorporated in our spreadsheet. Let's see if we can set it up. Now, I'll do mine with some different numbers. I'll say 50 meters per second at 45 degrees. And I think they just want it on level ground. Yeah, it's a baseball, so you're hitting it from ground level. All right, let's try that. All right, so now we're gonna call this 2D incremental with drag. Some of this stuff can be copied right over. So I'll still need the time, drag coefficient, mass of the ball, and the weight of the ball. But now, when it comes to the drag force, we need a little bit different formula. It's not based on the components anymore. It's going to be based on, it'll be velocity. So this is a vector drag. Yeah. Alright, now I'm not going to be able to get a vector into a column because I don't think Excel does vectors. So let's do one for drag force in the x direction. And then we'll do one, maybe I could call it horizontal drag force. And vertical drag force. So no vector. F drag x equals negative b times vx times the speed. And over here, F drag y equals negative b times vy times the speed. Alright, so how did I know to use those? Like, why am I using those? Let me explain. See, the drag force is a vector. But let's look very closely at these notations. Velocity has two components. But this is a magnitude of velocity, which is the speed. So it just has a single scalar number. You know. So if I were to rewrite it, you could say that F drag equals negative b times some vx in the I direction and some vy in the j direction. And over here, the magnitude of velocity is simply going to be just a square root of vx squared plus vy squared. So if I want, I could break it up into two components, where I would get that the F drag in the x then would be simply negative b vx times radical vx squared plus vy squared. And then we could have F drag in the y direction, negative b vy radical vx squared plus vy squared. So I'm just breaking it into two, and then these are the formulas that I'm trying to enter into my spreadsheet. We're going to need a column for Vx, but we also need like other columns. See, I did a drag force column, but then I did a net force column. So horizontal net force vertical net force. Alright, so the horizontal will simply be the drag. So it's just same as that. But the vertical will be based on F drag minus mg. we'll do AX for horizontal acceleration. And then we'll do AY for vertical acceleration. We'll do Vx for horizontal velocity and Vy for vertical velocity. Then we can have an X and a Y for our particle. Alright, I think we're good. So just like before, we tried to calculate, let's see, we did the drag force based on the initial velocity. So we better find those. Better find what the initial velocities are. So let me go back to mine. I mean, I don't even have to go back to it. I said that it was going to be, the initial speed would be 50, and then it'll be cosine 45, because I was just going to use a 45-degree angle. So 50 times sine of 45 would be the y. Alright. So we're talking about 35.36 for that one. And same thing for this one. So that gets us started with our motion. I'll put this thing on just the origin for now, because we're just hitting it from level ground. Alright, from those velocities, I ought to be able to calculate the drag components. Now we want for this negative b, which is negative aq10, multiplied by your x component, which is az10. And then here's the tricky part that trips people up. You can't just multiply by the absolute value of like Vx or something. But what you have to do is multiply by the current speed of the particle. So to do that, you could do square root of Vx squared, which for me would be az10 squared. And then you should add in the Vy squared too, which would be Ba10 squared. Let's try it on this one here. So we'll get equals negative AQ10 times BA10, which is my vertical velocity component, and then we'll do times the speed, which is square root of AZ10 squared plus BA10 squared. Alright, see how that compares to our previous drag force. Yeah, okay, it's similar. Before we were actually just going totally upward, now we're going at an angle. They're similar. Now let's get the net force. For this one, it's just going to be simply AT10. They're going to match for the horizontal. But for the vertical, it's a little more complicated. We got to do AU10 minus our mg column of AS10. Alright, we got our force. Now we want to use our force to find our acceleration. So AX equals F net x divided by m. So we want AV10 divided by AR10. Okay, strong acceleration there. Here we want AW10 divided by AR10. Okay, great. Now that we have our accelerations, we can use them to project like what our velocities will be in the next instant. For Vx, let's do our AX previous, which is AX10. That's really convenient that the column turned out to match the variable. Didn't expect that to happen. All right. Times 0.05 plus previous velocity, which would be AZ10. All right, for this one, same thing. I'm going to do AY10 times 0.05 plus BA10. Alright, now that I have those velocities, just like before, I can go on to find the new drag force. So if I just copy that column down, so I'll just copy that down, copy the net force calculation down, copy the acceleration down, and the process just keeps going. So we should be able to just drag all this. Okay, let's see what our findings tell us. Alright, so acceleration. If you check out the horizontal acceleration, you can see it's approaching like a constant velocity in that horizontal dimension. Now, let's see, for AY, it should head toward 9.8 at the peak. And all that, but yeah, that's when the velocity is 0, so that's good. And then it goes into like a terminal velocity type of situation. So I'll just quickly do the positions, and then we'll graph it, and then we'll see what it looks like, and then we're done. We want to do velocity AZ10 times 0.05 plus BB10 gives me my new X position. Here we'll do BA 10 times 0.05 plus BC10. Alright, so we're going upward. And I'll just make a graph of Y versus X. Simple as that. Vertical position versus horizontal position. Alright. So there is our projectile's path. Now I didn't include an example without drag, but you know what it would look like, right? It would be a parabola. It'd be a perfect parabola if it was without drag. So how could I make one just really quickly without drag in like 5 seconds? Easy. Copy the whole thing. Change drag coefficient to 0. Yeah. What it'll do is it will modify your entire table. And you can see what's happening. The AX is going to 0 when that happens. The AY is going to negative 9.8, which is what's expected. And let's just make them all zeros and plot that. See how it compares. So that's the beauty of like having your constants in the spreadsheet, because you can change them and then change like your final results with just making one simple change. It's pretty cool. Okay. Let's see what this looks like as a plot. Look at that. Perfect parabola.